All right, so we're going to start working on lecture 4 for data structures now. Today, we're going to be going over the list class from the STL, the standard template libraries. This is kind of similar to what we're going to do, or what we did last week with the vector class. You can't hear. Okay, hold on. The rest of you can hear me, right?
Right.
Okay, but McTiger can't. All right. I don't know what the issue is with McTiger. Let's see here.
Probably try leaving and joining back. Oh, you can't hear, obviously. Nice.
All right. Did you try turning it off and turning it back on again, right? So, okay. Sorry about that little mix up there. So, as I was saying, we're going to be looking at one of the STL classes today, the list, which is a linked list. And so we're going to kind of start off kind of doing some diagramming first. That's why we're over here on the whiteboard. And then we'll go into Visual Studio and just kind of mess around and write some code. I don't really have anything planned, so we're just going to kind of go off the cuff and see like whatever we write, that's what we'll end up with. We'll try to do a good portion of the functionality that you'll see in the lab tonight to some degree, so that you have a pretty good jumping off point there. Speaking of the lab, hopefully you guys saw that I put out an announcement today that I updated the DSA Labs project. So you'll need to re-download that because it'll have the Lab 4 stuff in there, which I wrote over the weekend because I'm a huge procrastinator. So, and Lab 5 is in there as well, right? So we've got Lab 4 and Lab 5 this week. And then on Friday, for campus students, we'll just have the midterm. I'm still working on refining the midterm because I've added in this new material. So as I mentioned in that announcement, I'll have the midterm available sometime tomorrow, Tuesday. But that's going to have everything up through Friday or up through Wednesday's lecture. So probably no one's going to want to do the midterm anyways. Typically people wait until the weekend or wait until Friday for campus because that's the only day they can do it. But most of the online students wait until the weekend to do the final or midterm and final for whatever reason, right? So let's go ahead and get started here. So we're going to kind of do like a compare contrast between a vector or array, right, and a linked list, and kind of talk about some of the benefits between both of those. I'm still trying to figure out which order I maybe want to do these pairs of lectures in. If I want to do, vector first and then you have you write the dyne array, or if we want to swap those. So anyways, so let's look at an array, right? So a vector is basically an array, right? And so we have some values, right? And this is again, right, it's a contiguous, right? So we're a contiguous we're contiguous memory, right? And so that means that it's going to be pretty fast to be able to access any particular element or piece of data in our vector, right? So if we, let's just say that this vector is called vec, right? So if I wanted to access this element here that has a 4, right, then we could say vec sub 3, and that is able to access that data, right? And that's going to be at an order 1 algorithm complexity, right? Because just like in a standard array, because that's what a vector is underneath the hood, it's just an offset, right? We talked about the memory offsets when we were talking about arrays last week, right? So we can jump to any particular value in our vector or any particular index at the same cost in time, right? It doesn't matter if it's way back in the array, or right, if it's like, you know, index 4200, it doesn't matter. It's going to take the same amount of time to get there because it's just an offset. Now, if we look at a list, right, a linked list, which we've talked about a little bit in PG2, right? I don't think we don't cover that in SPR anymore, but this is a node-based data structure, right? So we're storing that data non-contiguously. So we're going to have each piece of information is dynamically allocated individually, right? So with a vector, right, we allocate the whole block at once, right? That's the way that we do it with arrays. We allocate all of the memory we need up front, right? And then with the vector, right, we kind of get that added benefit that we can expand it, right? And there's a cost to expanding that, which we can recover here in a little bit. All right, I'm getting a little bit of power flicker here, so if I go away, we will reconvene when we can. So everything is moving around here. So I'm going to diagram this out and kind of explain exactly what all this stuff is. All right. Excuse me. So typically, let's say that this is our head and this is our tail. Okay. So how familiar are you with linked lists from PG2? Just so I can get an idea of where we're at here. Anybody want to fill me in? Okay. So it's not like an array in any aspect other than maybe that we're storing data, right? Which then we could say, well, and anything is like an array, right? So with vectors, right, everything is, let's write some notes over here. Everything is up front, right, for the most part, or for arrays, right? So array / vector. There's a big upfront cost, right? When I create the array, right, I'm allocating all of the memory up front, right? Let's just for the sake of simplicity right now, let's just assume that this is an array, right? So I'm just gonna cross this out and write array. So we allocate everything up front, right? So I have, say, dynamically allocated this memory here, right? This array, and so I can only store 4 items, right? That's all I can store with an array, right? A vector, a little bit different. We'll get into reviewing some of that stuff in a little while. With a linked list, there is no fixed size because we're dealing with non-contiguous elements, right? These things called nodes, right? So this right here, that's a node, right? A node is going to contain whatever data we're storing, so in this case an integer value, and depending on the type of list, it will have one or more pointers that point to other nodes. Now we won't have to create our own nodes today. We'll save that for Wednesday when we're writing our own linked list, but this is all going to be kind of handled internally within the list class, right, within the STL. So what that means is that, one, we're at a bunch of different places in memory, right? So again, if we were to say this vector, right, started at address 100, then the next element would be at 104, 108, 112, right? If we're dealing with integers here. Whereas a linked list, maybe this guy's at address 1000, this guy might be at address 2600, and this guy might be at address 5 million, and this guy might be at address 462 or something like that. So we're non-contiguous. Every single time I add something into my linked list, there is a call to new happening where we're allocating just space to store that one piece of data and the pointers to tie it into the rest of the list. So if I wanted to add something into my array, right? If I want to add in a piece of data to this array, I can't, right? Because this array is fixed size. It can store 4 pieces of information, and that's it. A linked list, we can add, depending on what functionality we have, to the front, the back, the middle of our linked list, right? So I could add in some other value, right? This is going to move this pointer over because that's now the end of the list, right? And so, and this is at address whatever, 1600. So we can expand the linked list very easily without really much overhead, right? If we think about let's say we have a vector, right? So I'm going to scroll over here. We got 3524. So let's say we have a vector, right? 3524, and I want to add in something else to that. Well, we know that we can do that with the vector, right? But we also know that there's a cost associated with that, right? Whenever we wrote this in our dyn array with our reserve functionality, right? We have to create a new array that's larger, right? For a vector, it's 1.5, so that would increase it to 6, right? And then it has to copy over all of that data, right? And then we reassign some pointers, right? We're not going to get all too into the weeds here. We're going to delete this, right? And then add in our new value, right? So every time I need to add something in and I'm at my capacity, there's a bit of overhead there, right? Like it has to go and dynamically allocate a large block of memory and copy over all of that data, right? And that is going to potentially be noticeable once we start getting into larger sizes, right? With a linked list, we don't have any overhead. So to add something to a linked list, it's an order one operation, right? No matter how many things we have. Okay, but to access information, depending on how we do this, right? So let's say, let's just say it's really basic, right? We don't have any type of iterator or anything like that, which we'll get into. So I don't know where this node is located at, right? Internally in my list, I'm going to have access to the frontmost thing, right? So I'm going to have access to this, and I'm going to have access to this, but I'm not going to know the address of anything else in the list that's in the middle because we're not contiguous. All right. So, right, it's not an offset based system like arrays. Okay. So that would mean that in order to access something, right, like let's just for simplicity or hypothetical, let's say that we had a bracket operator, right? So I wanted to access the thing that's at this third node, right? So that would mean that I would have to start at my head with some temporary pointer, right? So let's just say, how can I do this pretty easily? Let's move this over here. So say I have some temporary pointer, and then I'm going to loop and move it over in number of times, right? So if I need to move it over 3 times, I go 1, 2, 3 times, right? So that means that accessing things in my list would be order in, right? Because every time I don't know where any specific thing is at. So we would have to start at the beginning and follow pointers, right, over until we got to wherever we needed to be. All right. So that's bad, right? We say, well, vectors are better because they're order one for traversing through or accessing a random element, right? And lists are going to be order in, right? But we do have an iterator, so we can iterate through the list, right, and hit every single one of these just like we could with a vector or with an array, and that would essentially be about the same time complexity. So so if we don't need to just access some random particular thing, then and it's pretty much a one-to-one there. Now, for removing things, we're going to have a big benefit on a linked list. All right, so we'll go ahead and talk about that, and then I think we'll go ahead and jump over to some code and just again see where it takes us. We'll go back over this removal stuff on Wednesday because you're going to have to write some removal code when you write your own linked list. So let's say that I want to remove this value here from my vector. All right. So we know from working in the lab and seeing the lecture the other day that we have an erase function, right, within the vector, and we can get rid of some data, right? But the way that we do that, right, is by essentially copying over all of the data after it to kind of fill up that spot. So I'm just going to overwrite it here. I'll use like maybe a slightly different, slightly bigger marker. So we go, okay, well, there goes a 2, and this gets overwritten with a 4, and this gets overwritten with an 8, right? And then this one is like, can be rewritten, right? So that is going to potentially be a very expensive operation, right? Imagine like if we had a whole bunch of extra data over here, right? And we had to copy back, you know, hundreds or thousands of pieces of data. That's not very efficient. Whereas if we're over in our linked list here and we say, we've found that this is the one I want to remove. Then this is going to be an order 1 operation, right? The vector would be order n, right? Because it has to move over all of those elements. This one, we can just basically take our pointers to the guys to the left and right of us, if there are any, and right, say, okay, well, let's get rid of that and point this pointer over here, and then let's get rid of this and point this pointer back over here, and then I can delete this node, right? Because each individual piece of the linked list is dynamically allocated, right? So with the vector, right, I called new to create this whole array internally. With the linked list, I've called new 5 times originally because each node is dynamically allocated. Okay, so that means that linked lists are better in situations where we're going to have to remove things very frequently, right? Because removing out of a vector is not very efficient, right? So if we were thinking of game objects, right? Like we have, you know, bullets or enemies that are getting spawned and then they're getting, you know, killed, or the bullets are hitting a target and needing to be removed so that they don't update anymore, right? Then we would probably want to use a linked list for that, right? Whereas if we had something that was a more static, just we need to store a lot of data, we need to, and it's not going to really shrink in size, right? It's just going to grow. So we have, you know, like a bunch of accounts or something like that. Then we might store those in a vector, right? Also, sorting is much easier to do in a vector or a contiguous type of data structure, right? So an array or a vector, because a lot of the better sorting algorithms are going to assume that that memory is contiguous, right? So they can do that divide and conquer type of algorithms. And a linked list doesn't have that, right? Because we don't know the address of where any particular node is at. So sorting in a linked list is not that easy, right? It can be done, but it's not that efficient to do it that way. If you wanted to sort a linked list, I would probably write it so that it is always sorted, so that when you add something in, it slots it into the right place in the list, rather than just, adding it to the end of the list or adding it to the beginning of the list. All right. Any questions at this point with the diagramming?
I'm pretty good.
All right. So we're going to pop over to the code and we're just going to write some stuff and see what happens. So let's bounce over to Visual Studio. All right. So we've got just an empty project here, right? The list is just like vectors included in the vector file. List is included in the list file. So if you ever need to write a list, then that's where it's going to be. This is going to be another templated class, right? Just like pretty much all of the standard template library is going to be templated. Obviously, it's in the name, right? It's the T. So let's go ahead and create a list of, let's say ints, just for fun. And we'll call this, let's do summation. So we can have a little bit of an exercise today of just like writing a function. So, or actually, we'll leave that for the time being. Let's make it just, we'll start out without that first. So our list class, right, is just going to be a series of nodes, right? The internal, the list is a templated class, right? Let me get my data lab over here so that I know what we're talking about. So let's go ahead and add some things into our list and then print them out just for starters here. So let's add some data to the list. We'll use a for loop to do that, I guess. Less than. We'll add 100 things into our list. Why not? So, and we'll use random numbers because why not? All right, so just like the vector class, if we want to add something to the back of a list, right, then we call pushback, just like this, it's the same function, right? A lot of your data structures that are kind of more general purpose, like vector and list, have a lot of the same function names, which is great because then you could kind of bounce back and forth between them, and see what's more efficient, right? And maybe we'll run some timers here in a second to see if one is faster or slower than the other. All right. So we can add everything in, and then let's try to display them. All right. We'll use the list.size, right, just in case that size changes. And let's try to print them out like we did with the vector. So the vector, right, overloaded the bracket operator because internally the vector is just an array, right? But they do not overload that for for the linked list. So we need to use a different method in order to access that. All right, and that is going to be, how would I access everything in my list, you think? Right, what would be a way to do that if I can't use the bracket operator? Okay, so we use the same kind of approach with the vector class and some scenarios, right? We used an iterator. So that's what we're going to do here, is create an iterator, right? And set it equal to the beginning of our list, right? Just like we did with the vector, right? When we were doing that erase, although we did change it to a while loop, right? But we're not removing anything here, so it should be all right. All right. So basically what this iterator is doing, much like the iterator in the vector, right? So if we had our vector here, right, let's say I've got my vector and I'm storing some values, right? 3, 5, 8, 2, right? Then the iterator starts here, and then it basically, the iterator is the address of where this 3 is located, right? And so that's why we have to dereference it, right? And then when I increment that iterator, it moves over one element, right? So it increases that iterator by 4 bytes. With the linked list here, we're going to start out here, right? That's the beginning of our list. And then the iterator, rather than just moving over 4 bytes, it's going to move over to the next node, right? So it's going to follow this pointer to go over to the next thing in the list. So regardless of where we're located in memory, right? And then it would go over to this one, right? So just so that the functionality wise, right, most of this code is like the same. We could swap back and forth this code between the list and the iterator very easily. Or I'm sorry, between the list and the vector very easily. So if we run this, right, okay, so we printed out our 100 values, right? Let's see how long that took us to do, right? Let's do a comparison, compare and contrast between the vector and the list, and see if one is better than the other at just adding in data. All right, so I'm going to include a little timer class that I have written. So I am going to, at the beginning here, I'm going to start my timer. I'm going to run through my loop, and then I'm going to stop my timer, right? And we'll say adding took that long. So this, I'll go ahead and go over this timer class real quick. A very, very simple little timer class. And timing your code can be a way to see if it's optimized, right? So this timer class basically has two data members. It has a begin and an end, right? And then inside, whoops, where do we go here? Right here, right? Whenever we start the timer, we set the begin variable to the current time, right? So this what this function now does is it basically sets this to the current time. And then when I stop, I set my end to the current time, right? And then when I call elapsed, it basically just gets that delta, right? So I take the end minus the begin, and then I convert it into a couple of different times, right? Milliseconds, microseconds, and nanoseconds. So it's all the same, right? But sometimes a function call or a loop might run for less than a millisecond, right? So so we're going to have these smaller time spans as well, just in case. So we'll say adding, and then we'll say displaying. We'll do the same thing. So we'll say timer.start, timer.stop, and then we'll say displaying. I think we'll need throw a couple of lines in front there, and then we'll do timer.elapsed. We'll see what this runs, right? So it took me to add 100 things into my list. It took me 117 microseconds, right? And then to display them all, it took me 30 milliseconds, okay? So let's write that down just so that we can do a compare. So we have pushback took me, what did we say? We said 117. Where is this? 117 microseconds. And then to display, we said that was basically 31 milliseconds. Okay, so now, just for fun, let's see how that would compare if we did that same operation with a vector. Okay, so all we have to do, right, is, let me just change this to vector, right, which changed our iterator to a vector. What I did there, right, is if you have a variable or a type or something, and you want to change it in all occurrences, right, then you can click on whatever your variable or type is and hit Control R, and that's going to get you to this rename pop-up, and then you can just change it there, right? And it's going to basically do a smart find and replace to change everything over, right? Actually, this is bad because it's changing things to, okay, I don't want to do that. Never mind. Don't do that with a type. You can do that with this. Like if I wanted to change it from the list to the vector, right? Then that's good. If I was changing list, then that was actually going to go into my list class and change it to vector, which would be bad. So I actually want to just change this to vector here and change this to vector here. Right, and now we're back where we need to be. Right, we'll compile this and we'll run these times. Okay. So we can see that adding took quite a bit smaller amount of time, right? If this is the list and this is the vector, right? Push back took me, instead of 117 microseconds, it took me 42 microseconds. So it's faster to add things in, right? And it was actually faster to display as well, right? So if I was just adding a bunch of stuff and displaying, right, then maybe the vector is going to be faster, right, for some particular size, right? Let's see if it changes if we go to a bigger size, right? So let's just look at the, oh my gosh, I printed everything out. Okay, so let's look at the adding, right? So adding 2 milliseconds, right? So obviously we know this is probably not going to be good if we're a list, right? Because we're calling new a lot, right? So actually, I won't even print all this stuff out. So we were what, 2 milliseconds, I believe was. This is 8 milliseconds, right? So it's a little bit slower to add things in, right? But that's because the vector is very, very optimized. The linked list is optimized as well, but they're probably doing a lot of things behind the scenes to shift that memory around pretty efficiently. All right. Now, if I want to remove things, that's probably where I'm going to see my list really have some payoffs. So let's go ahead and let's not make them random numbers, because then that would throw things off, right? If you're trying to do some timing, you want to make sure that your data is the same between both things, right? So let's say that I want to push back. Let's just say I'm going to push back I, and let's erase. Let's erase even numbers. Let's say that. So let's go ahead and let's say we're going to erase even values. So we'll make our iterator here same way that we did the other day. So that means that this way, right, where we said while our iterator is not at the end of the list, right, we'll do some comparison, right? So we'll say, hey, if iter mod 2 is equal to 0, then I want to erase that object, right? Otherwise, I want to move over, right? This is like the same thing that we did the other day. Let's change this back to 100 just to make sure that it works, right? So, right, because I don't want to look at 10,000 pieces of data, right? So it looks like we removed all of our odd values, right? And that took me 9 milliseconds. It looked. Oh no, that's the display, right? We want to look at erasing, right? So see out erasing. Same thing. Timer dot start lowercase. Timer dot start. Timer dot stop. Timer dot elapsed to print that out, right? So the erasing here for erasing every other one, right, took me 150 74 microseconds. So we'll kind of write that down. We can put it here, right? So we'll say erasing. I forgot what the number was already, so I'm going to run it again. 155. It's going to vary like slightly because, you know, I'm running other stuff on this computer. So, you know, so we can try to just get a ballpark. 178, 101. So we'll say it's like about 150, somewhere in that ballpark there. And then let's look at how that would be in the vector. Let's see if that's any more or less efficient. So we'll change this to vector, and we'll change this to vector. Again, all of the functionality, all of the function names are the same. Internally, they're doing different things, right? We're going to see here, maybe, looks like the vector is still faster, right? So, so it looks like the vector might be a little bit faster still on this particular thing, right? We can't say that it's always going to be faster for all data types or for all amounts of data, right? So, but it's a good idea when you're working with a problem, right, is to do some type of compare and contrast to see what's more efficient in any given situation, right? We could also see, right, potentially what the memory usage is, right? So if, let's say, before we erased anything, so after, that would be right up here, right? So before we erased, if we were to print out the list dot capacity, right, then that's going to be, right, the number of elements that we have allocated, right, which for our vector is 141, right? So even though I'm only storing 100 pieces of data, I'm allocating space for 141. So depending on what the size of my objects are, that could be a lot of memory, right? If it's integers, that's probably not a big deal, right? Because integers are 4 bytes. So whatever 141 times 4 is, so I'm wasting 564 bytes, so about half a kilobyte, right? If we were to go back to say, hey, let's make this a list again. And make this a list, right? Well, there is no capacity in a list because it only allocates the amount of things that we've actually created, right? So we have size, right? What's max size? I'm not familiar with max size. Max size, where it turns the maximum size on my list. So let's see what that is. Oh, that's the total amount of things that I could actually allocate. So that's not how many I actually have allocated. I actually have allocated 100 things, right? It should say 100 right here, right? So we don't have that like extra space like we do in the vector. So that might be an instance where we might choose one over the other as well, right? Because we don't want to eat up a bunch of additional memory that we're not using. Okay, so let's go ahead and let me see here. What do I want to do? So let's look at inserting something. Okay, so we didn't do any type of insertion with the vector class, right? But it is a piece of functionality that we do have. So let's get rid of this erasing stuff for the time being. Just we'll comment that out as well. And let's add something into our list, right? So we know how to add via push back, right? And that's just going to add the data to the end of the list, right? Or to the end of the vector if we were using a vector, right? Now, if I want to insert something, right, then there is a function that will do that. It's called insert, right? And it's going to have a couple of different overloads. But we can see via, why's my IntelliSense popping up way down there? I don't know why that is. But it's got 5 different versions of that function, right? So, but they all take in an iterator, okay? So the iterator lets me know where I want to add that in at, okay? So let's say that I want to create an iterator, right? So where's my iterator at? It's up here. We'll bring that guy up. So let's say that I put my iterator at the begin, and then let's increment that. Okay. So now my iterator is pointing to the node that's storing 1, right? And we could demonstrate that. Let's comment out all of this stuff for the time being. If I said C out the dereference of iter, right? Then we got 1. We'll turn that timer stuff off as well. We'll just turn that off. So I'm pointing to the 1, right? And if I was to, increment again, then I would be pointing to the 2, right? So let's add something in at that spot. Let's insert something there. So we'll go ahead and call the list.insert, right? And we'll just add one thing, right? There are versions of insert where we could add in a group of things, right? If we wanted to, right? But we're just going to add in one thing. So it's looking for the iterator, and then it's looking for the value that I want to add. So let's add the value, I don't know, 500 in. All right. So we're going to insert in at the iterator that value. All right. So this is something that throws a lot of people off, is it inserts it at that spot. So it inserts it essentially in front of wherever our iterator is located at, right? So our iterator was at the 2, right? And we insert in front of where we're at, right? So essentially, if we think about the linked list, right, as like elements in an array, right, where this is like sub 0, this is sub 1, this is sub 2, I inserted into sub 2, which pushed everything back, right? So we always insert in front of wherever our iterator is at. Okay. Any Any questions on that, on insert?
No, the only question I would have is to how to actually write an insert.
Okay. So we're definitely going to go over that more in detail on Wednesday, because you're going to have to write a linked list. And so I think we'll diagram things out that day. So probably I'm thinking this lecture might be a little bit short today, and then Wednesdays is going to be a little bit long. Like I said, this is the first time I'm running this lecture, so I'm not 100% sure like what all we need to do here besides just talk about the class and what needs to happen in the lab tonight. But on Wednesday, right, we'll definitely go over like how to add things into lists, how to remove things, how to insert things in really fine detail.
All right.
So let's go ahead and let's see, what else can we do here? I know there's other stuff we can do. So removing, right? We looked at erasing things, and that's fine if you want to erase a particular thing in the list, right? But sometimes you may want to say, add a bunch of things into the list and then iterate through and remove them one at a time, right? So thinking of like a queue, right? You guys know what a queue is? Right? So a queue is something that is first in, first out, right? So a queue is FIFO, right? First in, first out, right? So if we have a bunch of data, right, that we want to add in, like let's say that we have this set up for something like a, I don't know, like a print queue, right? So I've got a printer, right? And maybe it's networked, right? And so a whole bunch of people in the office decide to send print jobs to this printer, right? So it has to store all of those print jobs temporarily, right? And then it has to actually perform the operations and print out the documents. And it's typically going to do that in a first in, first out type of system, right? There's not any like priority, right? Like your boss doesn't get to move his print jobs to the front of the queue, right? Because his username is manager or whatever. So, I mean, I guess we could have software that does that, but typically we don't, right? So they just have to kind of wait their turn. So we've already added in a bunch of stuff, right? Up here, right? We added in some things. And now I want to remove them basically in the order that we inserted them, right? So actually we could set up some user input to make this a little bit more interesting. Yeah, let's set up some user input here. So we'll do a completely different example. So I'm going to turn off all this code. And we will use temp, and we'll use a list of ints. We'll just call it Q. And let's set up ourselves a little menu here. Switch on choice. And so we'll say case 1 is our adding. So that's going to be a push back, right? I guess we need to figure out what we're adding, right? So we'll say enter value to add. Oops, that should be C out. What am I doing? I think I knew how to program or something. CN into temp. We'll just assume that people type in the right information, right? We won't error check this. And push back is how we add something into the list, right? And then we'll of course break out. That's case 1. Case 2 would be removing. Or we would say temp equals q dot front. Okay, so there's a function inside of the list, right, which will get the data at the front of the list, right? So I need to get that data because if I call this next function, it's going to remove it from the list, and that's pop front, right? So this is remove the data from the front. So we'll need to call front to get the data before I pop it off, right? And then we can say the value removed was temp. Right. And then down here, let's see, where is, that's my switch, that's my thing, so I can put here, this should be, actually I could do this up here, right? If 0 is equal to choice, break out of my for loop, right? And maybe we have the screen down here, like a system pause. Something. This is all doesn't look right. This. Oh, I'm missing a ending curly brace for my switch. There we go. Let's move all those guys over. Like that. Okay. So this right here, let's talk about this for a second. This is a kind of a weird way that I wrote my if, right, is I put the constant on the left. This is what we call a Yoda conditional, right? And what that is going to protect me from, because I've seen it, I don't know how many times over the course of being a teacher, right? And I've done it too, is you'll do something like this, right? Where you'll space out, or you won't realize it, you're tired or whatever, and you'll put a single equals instead of a double equals. And what that's going to do is that is going to assign choice to 0. So regardless of what I typed in, wherever my input is, which I didn't even put any input here. See out menu option. Maybe I should probably see an input choice. Right. So regardless of what I typed in up here, it's going to set choice to 0, and therefore I'm never going to get into any of this because I only have case 1 and case 2, right? And I'm not even going to break out because 0 is false. So I'm just in an infinite loop here, right? Like if I run this, believe, let's put another new line here. So if I put 1, oh, oh, because I have it up here, right? So if I put 1, then I exit out of my program, right? Because this broke me out, right? So like if we change this to a while true, right? Then I'm never gonna leave, right? 1, 2, 0, right? There's no way that I can ever leave this program without actually just like closing it out, because this here is actually assigning choice to 0. Okay, and again, that's something that happens, right? We all do it, right? And then we feel like complete idiots when we ask for help and someone says, oh, you've got a single equals instead of double equals, right? So what you can do to fix that is put the constant on the left, because now syntactically this is trying to assign choice into 0, which is not legal, right? And so if we compile this, we get a compiler error that says basically that we're using an assignment instead of an is equals. And now we can put that other equals there, right, and fix it, right? So before, when I had the single equals, when I had choice equals 0, right, there's no compilers, there's no warnings, there's no errors, because that is completely 100% valid code in C++. So it wasn't causing any issue. I'd have to actually debug it and try to figure out what's going on, right? Run through this line by line. But putting the constant on the left will, like I said, will give us a compiler error if we don't do the double equals. So that's a nice, easy way to make sure that you don't make that single equals double equals mistake, right? And they call this Yoda conditional, right? Because Yoda talks backwards. So the if is backwards, right? And so that's a real term. You can Google that. I'm not witty enough to make that up myself, right? So so now, right, we say add a value. So we'll add in 5, and then we'll add in 2, and I'll add in 7, right? And then we'll remove a value, right? It's going to remove them in the order that we added them, right? So the value removed was 5, and then let's add an 8, right? And then we remove the 2, and the 7, and then the 8, and then there's nothing to remove. So we're crashing, right? Because we're calling front on an empty list. We can check that, right? We can say something like we could do an if in here, right? Like, hey, if q dot empty, right? If we're empty, then say nothing to remove, else do this other stuff, right? And that way, if the list is empty, right, we won't crash because there's nothing to remove, right? So we could add in 1, 2, 3, remove 1, remove 2, remove 3, right? So that's a queue ordering, right? It's first in, first out, all right? And so we're using push back, right? Because that's pushing an item to the back, whatever data type we want to store, right? And then we're using front to get the data that's at the front. And then after we've gotten that value, and we do whatever we need to do with it, then we can call pop front, which is going to remove the value that's at the front of our list. All right. So any questions on that? Okay. So I'm not going to do this, right? But I'm just going to make a little note here. So we've seen stacks before, right? So a stack is has a different ordering sequence, right? That's first in, last out, right? So for that, right, you're going to have a part of kind of emulating a stack in the lab tonight. So I can't, go over all of the details on that, right? But it's first in, last out, right? We do have a function instead of push back. There is also a push front if you need it, right? Obviously, we don't want to do that here, right? But that function does exist. You may or may not need to use that depending on how you implement your functions tonight. Okay. So let's do a little bit of critical thinking here, just for fun, right? So get the summation of a value. So who is messaging me? Someone is messaging me. All right. So do we know what summation is? Right? Math. I'm not a very big math guy, but we'll try to write a function, right? We'll make it a long just because. So summation is basically going to be like if I wanted the summation of 3, right? I think like the symbol for summation is like it's not an E, but it's like that weird Greek E looking symbol, which I don't know the ASCII symbol for that, right? But if I wanted to get like let's say the summation of 5, right, then that's going to be 5 plus 4 plus 3 plus 2 plus 1, right? So it's kind of like a factorial, except with addition instead, right? So there's a couple of ways that we could write that, right? How could you write a summation function?
I have no idea.
Okay. So Tiger said we could use a for loop, right? So yeah, absolutely, right? So we'll just use this as an example, right? So what would this be? 9, 12, 14, that would be 15, right? If I'm doing my maths right. So we could do I equals 1, right? I less than equals n, right? Plus I. And we can say sum equals 0. It's sum plus equals I, right? And return the sum. All right. This is probably one way to do it. Let's go ahead and check and make sure that this works, and then we'll look at a different way that we can do that using recursion, because recursion is fun. Okay, we'll remove that. So we'll say and sum equals summation of 5. We'll just make sure that that prints out 15. It would help if I actually printed it out. So 15. All right, cool. So now how could I maybe do this without a loop? Is that possible? So we can use recursion, and you probably, I think you guys go over recursion like in PG2, but then I don't think you really cover it in systems programming, right? So recursion means that we call the function again, right? So that's for us in programming, that's what we think of when we think of recursion, right? Is that it's a function that calls itself, okay? And recursive functions need to have an exit condition, right? So that they don't just call themselves over and over and over until the program crashes, right? So our exit condition here would be if n is 1, then I'm going to return 1. All right. Otherwise, I'm going to return n plus the summation of n minus 1. All right. And let's see if this works, if I wrote this correctly. All right. We should still get 15. We still get 15. All right. So what is actually happening here? Well, let's jump over to the whiteboard so we can kind of diagram this out. So we'll just we'll jump over here. I guess that's the end of the whiteboard. So if we have something called a call stack, right? And this is basically where we're at in our program, right? So our call stack starts out at the bottom where we have a call to main, right? And then main calls summation with the value 5. Okay, so our function, right? Well, I'll go ahead and rewrite it here. So it says int. I'm just going to say sum just for brevity, right? It should probably return a long. We'll return a long. We'll fix that over in the code as well. And we say If 1 is equal to n, return 1. Otherwise, we're going to return n plus the sum of n minus 1. All right. So when I call this function, right, we're going to come in, right? We're going to hit this line. N is 5 right now. So we're not going to get into the if, right? So we're going to move down to this line, right? This line has a function call in it. So we're going to have to call that function, okay? So that's going to go onto the call stack. We're going to call sum of 4, right? So again, so now we're going to start, we're going to go back to the top of the function again, right? Okay, well, 4 is not 1. So we'll come down here. And again, we have a function call. So we're going to call summation of 3, right? So we'll come back in. 3 is not 1. Go to this line. It's got a function call, so that has to happen first. So we're going to call summation of 2. Same thing. And then we're going to call summation of 1. And that's going to now trigger, right? So n is equal to 1. So I get into the if, and I return 1, right? So this function here, this guy right here, returned 1 to the previous function call, right? So this is now going to get removed off of the call stack. And we can think of this right here. So this right here evaluates to 1, right? Because this function returned 1. Okay? Now, n right now, n is 2 in this call. So I'm going to return 3, right? 2 plus 1 is 3, right? So now this gets popped off the call stack, right? And this is 3. So n is 3, so 3 plus 3, and we're going to return 6 to that guy. Right, and this is going to get removed from the call stack. And so now n is 4, and this returns 6, right? So therefore we're going to return 10 to that. And then this is going to get popped off the call stack. And then now we have the final call, right? Where this is 5 and this is 10. And then so now we return 15 to main. All right. So recursion is a very easy way to do some things very very elegantly. We'll end up using recursion on Wednesday, right? I don't think we won't need recursion today, but I figured any chance we could use to do a refresher on recursion is good. It's an extremely valuable tool that you can do a lot of stuff with, and several of the later labs, like I said, the linked list, and the binary search tree are going to make heavy use of recursion. All right. So any questions on this recursive function that we wrote here? All good, right? We could actually turn this into a one-line function if we wanted to, or a one-statement function. If we go return n1 is equal to n question mark 1 colon that. Is that going to work? All right, so this right here, I don't know if you guys have gone over the conditional operator. So I'll go ahead and bring us back to what we had here, right? We could even do something like this. Return 1 is equal to n question mark 1 else n plus summation 1. So the question mark colon, if you haven't seen it before, this is called the conditional operator. So question mark colon is the conditional operator, and it's essentially an if-else. So this is the only operator in the language that takes 3 parameters or 3 operands, right? Most operators, like is equals, that's a Boolean operator, right? Because it takes a left-hand side and a right-hand side. This actually takes like 3 things, right? This first parameter here is our conditional, right? So whatever this is, it has to evaluate to a Boolean. And then this is, if that is true, it'll evaluate to this, right? So if n is 1, then this whole thing evaluates to 1, right? So we just say return 1. If this is not 1, then it comes over here and it does this code, right? So basically all it is it's just a way to condense an if-else into a single statement. I would use this for only like simple things, not anything complex, right? So this is probably a good example of a place where I might use this operator, but it's not an operator that you ever have to use. But it is one that can maybe potentially save you some time, so you don't have to write, like an if else, right? So just another tool for the tool belt, so to speak.
So what is faster, using summation, no, using recursion or not using recursion?
That's a good question, Hunter. Can we test that?
Yeah.
Yeah, because we have a timer, right? So let's go ahead and do that. Let's even make it like a bigger number, right? So let's say, like, I don't know, say the sum of 100, right? And we can do t.start, t.stop, t.elapsed. So we'll check it out during using recursion. All right, so that took me 26 microseconds. Let's see. Whoops. We don't need that. Should be the same. Yeah. So somewhere between 20 and 30 microseconds. And then if we were to do this using not recursion, using a loop, see how fast that is. Much faster with the loop, isn't it?
Yeah.
So, so some things can only be done recursively, right? Or done recursively uh, much simpler.
Right.
So, and we'll see some of that when we get into the lecture on Wednesday. Definitely, like when we go to copy one linked list to another, which I don't want to get into right now. Um, that is much simpler to do recursively than it is to do with a loop-based implementation. But yeah, this version is way faster, it seems, right? Which I mean, it kind of makes sense, right? Because we're not having to deal with adding all of those calls to the call stack, right? It's just able to just do everything within one function call. So might just be that the recursive version is kind of the cool kids way to do it, right? Even though it might not be the fastest way to do it, right? So,
Okay.
all right. So I guess let's go ahead and just start looking at the lab, and we'll answer any questions that that may pop up off of that. Um, so um, I'll just bring this over here. All right. So so just like the vector lab, we're going to have a kind of a, I don't know what to call it, so I just called it DSA Lab 4. Where we're going to just have a series of functions that we're going to write to pass some tests, just like every other lab in this course. So we're going to have a list of floating point values called mlist, and that's what we're going to be working with throughout all of these functions that we're going to write. Okay. So the first two functions here are kind of similar. They're going to take in an array and the size of the array. So kind of like our fill function from the vector, right? And we're going to add all of the values from this array into our list using either queue ordering or stack ordering, right? So probably like the majority of these functions will probably be very similar, but we're just going to add things in a different order, right? And then you'll want to make sure that the list is empty before adding values. Don't worry about this capacity thing. It looks like I copied it over from the other project or from the other lab, right? So there is no capacity within a list, right? There's no shrink to fit function. There is a clear, right? So that's what basically you'll want to clear out your list before you add anything in. All right. And then we've got another pair of functions. This one is just going to remove a single value and return it using, again, either queue ordering or stack ordering. So again, these functions will probably be fairly similar, right? But we're just looking at, adding things in kind of in the queue ordering and removing with the queue ordering or with the stack ordering. All right. Any questions on like that? I think they should be pretty straightforward functions. And again, we've done something similar already with the fill from the vector lab. All right. So moving forward, we've got a couple of different insert functions. So this one is kind of just is not a very efficient way to do it, but I kind of wanted to see to show you like how it's actually operating behind the scenes. So we're gonna pass in an index, right, of where we want to add. So if we think of this kind of, obviously you're not going to see this in your code because I'm not going to re-upload this. But if like this was index 0 and this was index 1, etc., right? Then I'm adding in, inserting, right, to this place. So what you're going to need to do is you're going to need to create an iterator and move over in your list however many spaces this is, right? And then call your insert function, right? So then, right, this is 1, 0, 1, 2, 3, 4, 5, right? So we inserted this 7 at index 2. All right. Now for this other insert function, right, we're taking in an iterator. So this one's going to be a little bit simpler because the iterator is already going to be at the place to insert, and so you can just insert at that location, right, by calling your insert function. This last function here is I was trying to come up with a kind of a critical thinking problem, right? As you know, right, a lot of programming is really problem solving, right? Like you're given a problem, you know the language, you know what tools you have, and you need to figure out how to solve that problem with the tools, right? So I was trying to come up with something, and I hopefully this makes sense, right? So we're going to have a list, and we're going to pass in a floating point value that's going to be something less than 1. So it's going to be just a decimal value, and we're going to want to remove every value from our list that has their decimal value is less than this one. So the int portion, the whole number portion, is to be completely ignored, right? And we just want to remove any values in the list that have a lower value, right, past the decimal point, right? So in this case, if I passed in 0.45, then 0.28 would get removed, right? Because the 0.28 is less than 0.45. This value would get removed from the list, right, or erased from the list, right? Or I'm sorry, these would not get removed. My bad. I have this backwards. So this would not get removed, right? Because we're only removing values larger. This would not get removed. This would get removed because 0.498 is greater than 0.45, right? So the trick here, right, is to figure out how to do that comparison, right? How can I take 498.28 and compare it against 0.45 to determine if we need to remove it or not, right? So you're going to have to figure out how to basically isolate just this portion of our integers to compare against. All right. So that's going to be like the tricky one for tonight. The rest of these are pretty straightforward, right? I think we did most of that stuff in the lecture today, right? And then we're going to return the number of values that were removed. So in this case, right, we would return 2 because we removed these 2 values from our list. All right. Any questions on that, or any way that this needs to be reworded or re-explained?
For the insert, we're actually making an insert, Craig. We're not calling the pre-written insert.
No, you will call the pre-written insert in both of these.
Okay.
Yeah. Yeah. On Wednesday, when you write your own linked list, that's when you'll write your own insert code.
Okay.
So yeah, this vector lab and this like basically not every other lab, but all of the labs that are using the STL, like vector, this one, and then next week you'll have another one on a class called unordered map. All of those are probably going to be a little bit easier than the other labs where you have to actually write your own versions, right? Because
Right.
all this stuff is like built in, right? And you just have to like call the existing method, and then on like on the DynaArray lab, you had to write what that method is actually doing. So that's going to be a little bit trickier.
Okay.
But does this make sense for the few of you who are here live for the lecture?
It makes sense to me.
Okay. Yeah. Hopefully I tried to give you like a good example here with a few numbers so that you could understand that. Everyone else in the chat saying yes. So I guess I did an okay job. I struggled trying to write this out yesterday in a way that made sense. So I guess I did all right. So, okay. If you don't have any other questions, then I guess we'll go ahead and call it. Again, if you, yes, Tiger, you will have to re-download the DSA folder. So I updated the thing on FSO, and I also sent out an announcement. So I don't know exactly how announcements work on FSO because I don't get the announcements. So I guess you get an email, right? But yeah, I did upload this back to Lab Project, right? If we go to preview, so you can see what I'm seeing. If you go to Lab Project, I did update this, or not that one, Lab Project. I did update this today, right? So this should be this is the new version. And then, like I said, I also sent out this announcement, which has the new version as well. So you're going to want to grab that, and then I'll have to update it again for next week, right? Because I need to write another lab that's not in there for next week, and then another lab for week 4 as well. So, yeah. So I would recommend when you re-download that, download it to a different spot, right? Because if you overwrite your wherever you have it located now, right, you're going to lose your DynaArray.h and your DSA Lab 2 and your well, you wouldn't lose the debugging, right? But you'd lose those 2 labs. So if you needed to go back and reference them, so I would recommend unzipping it at a different spot. That way you don't lose that stuff. And then I guess you could overwrite, the blank versions with yours, and then you can delete your old one, right? But I just don't want you to lose any of your code. I guess you could go back and download it from FSO if you needed to. So just in case. So also, right, if you need to, right, you can always go to the MSDN docs for the list class if you need to look up and see if any function exists that you might need to use in order to do any of the stuff you need to do for the lab. If there's maybe something we didn't cover, or in general, like if you were using this for your own project, this might be a good spot to look at and see what functions there are and how they work, right? So, so Microsoft provides really good documentation for you. All right. So yeah, I guess that'll wrap it up. It's a fairly short one today, but I'll make sure that Wednesday will be a long one because there's a lot to talk about with linked lists when you're actually writing your own. So buckle in for that one because that'll probably be a good 3-hour one. All right. So yeah, guess we'll see you guys on Wednesday. Thanks for coming.